So first I will recall what is Thurston metric in Teichmüller space. So let's say fix a topological surface, a closed surface of some genus bigger than 2. So the Teichmüller space of S is a space of marked hyperbolic structures on S. Up to isotopy. And given 2 elements in here, so for G1 and G2 in here, I can compute the following number. So it's the Thurston distance between G1 and G2 would be defined to be the log of the sup over some class C, which I will define now, of these numbers. So L G2 of C over L G1 of C. So where so this class here is a class of free isotopic classes of closed curves. Closed curves in S. And then it's the length function. So the length of a given class with respect to a point in Teichmüller space is the length, defined to be the length of the hyperbolic geodesic in this class. So the geodesic, length of geodesic, of the unique geodesic in the class C. So the picture is sort of like this. So I have a topological surface. And I have an isotopic class in there, which I will draw as a curve, but it's just a family of curves. So this is S. And when I pick my point in Teichmüller space, this gives me a, so this is SG. It gives me a very nice geometric structure on it, on the surface, and selects one curve in this class, which is the unique geodesic in this class, and I compute the length of this. So one can really see that this number satisfies the triangle inequality. And so I guess the theorem by Thurston, which says, so this number is greater or equal than 0, equality, so separate points, meaning that if I take 2 different points in Teichmüller space, this number will be strictly positive. And he also finds examples, so I will write it like this, examples of G1, G2, so that when you compute the distance from G1 to G2 is different from the distance to G2 to G1. So it's really asymmetric. So the goal of the talk will be to discuss an analog of this in some spaces of Anosov representations. But before doing that, I will try to state, maybe in a very vague way, some results that Thurston proved of this, about this metric, which I think it's cool motivation. But before doing that, let me just give one word on why this number should be non-negative. Okay, so why is it? I mean, I won't give a proof, I give a hint on why. So something that one can do is for a point in Teichmüller space, I can compute its entropy. So this will be the limit, means t goes to infinity, of 1 over t, the log of the number of classes, so that the length of C less than or equal to t. So we saw this kind of numbers appearing yesterday in Giuseppe's talk. And there is a fact that, so in Teichmüller spaces, there is a fact, so this is a very weird way of writing one, the fact. I mean, for all G. I mean, you have to prove this, but thanks to this, you can show that the Thurston distance is not negative. It's because if it was negative, it would mean that there is some k less than 1, so that the sup over C of LG2 of C or LG1 of C is k, so less than 1. And this would produce a strict domination between the market length of G2 and the market length of G1, which would say, if I'm not mistaken, that h of G1 should be less than or equal than k times h of G2, and this would be strictly less than h of G2, which is a contradiction. So in some sense, constant entropy blocks the possibility of this number to be negative. This is the entropy of the geodesic flow, the topological entropy. So some features, and I will be very vague, this is just as a motivation, some features that Thurston proves. There are many things going on in that paper, so I will probably forget. I mean, don't take this as a summary of what Thurston proved. I mean, just. So one thing is that, so there is another quantity that you can define for a pair of metrics. So if you have a pair of metrics, you can consider the maps going from the first metric space, let's say, which is the metric associated to G1, and the second one, right? And you can compute the Lipschitz constant of this. So you can compute lip of psi, which would be defined sup with x different from x prime of the distance associated to G2 psi over this. And so if psi is isotopic to identity, you see that this number has to be, that number has to be less than or equal than this, right? So in particular, if you compute all possible Lipschitz constants of maps isotopic to identity, then you get a bound, an upper bound for this. What I want to say is that dth is less than or equal than d lip. Okay, so this is defined as the infimum, the log of the infimum. So I consider all maps isotopic to identity, and I consider the Lipschitz constant. So this already is a good thing, because it tells you that if I want to find an upper bound for this, I just need to compute the Lipschitz constant of a given map. And if I want to find a lower bound for this, I can just find one curve that grows by some amount. But the really cool thing is that, so the theorem is that these numbers coincide. So I guess that this is maybe one of the main theorems of that paper. And there are, as I said, oh no. And as I said, there are many things going on in that paper, and I maybe just quickly summarize some of them very quickly. So I think that the basic ingredient to show that theorem is Thurston gives an explicit construction of geodesics for this metric. They're called straight lines. He also gives a very geometric construction, so explicit geometric construction of an optimal map, of an optimal Lipschitz map, homeomorphism, optimal Lipschitz homeomorphism. He also proves, let me just state it like this, he stated like this, so supremum simple. Meaning that he shows that, so, okay, the definition where it was here. So, to compute this asymmetric distance, you need to consider all isotopic classes of curves, but he shows that this is the same if you only consider simple closed curves, okay? And maybe one more thing. He also gives an infinitesimal version of this metric. So he defines for a vector tangent to Teichmüller space. He defines the Thurston norm of this vector to be the sup or C of the derivatives. So this is a G of the length function associated to a curve over the length. All right, so here I range over a matrix and I take the derivative at G. So I compute the length for a given C. I range over a matrix, I take the derivative over C and then over G and then take the sup of C. So he proves that this is a Finsler norm. So Finsler norm. By this I mean it's greater or equal than 0. It's 0 only if the vector that you put here is 0. It's homogeneous with respect to positive scalars, and it satisfies the triangle inequality. And moreover, the induced metric, so the path metric induced by this is DTH. So path metric equals DTH. Okay? So I guess this is not.
So can you repeat what is dg LA of C?
Right, so you take this, so you consider, so for a given C, you take this function. The dot is the. Oh, it's a dot. It's a dot. Sorry, it's a dot.
It's a bullet.
How do I do this? Yeah. So I take the derivative of that function at
okay.
Yeah. Yeah. Okay. So let's state result. Did I do this correctly? I think so. Okay. Right, so results. So to motivate how do you state the result, I will just give a different, some sort of different, it's the same number, but a different description of this metric. So we know that Teichmüller space identifies with a connected component of the space of morphisms of the fundamental group into PSL2R up to conjugancy. And there is also an identification between, so this takes some metric into some representation. And there is also an identification between the set of isotopic classes and conjugacy classes in the group. Which is taking some C into the conjugacy class of C. And so when you do these identifications, you see that the length with respect to C of a given metric can be computed out of the information of the eigenvalues of the curve gamma C with respect to this representation. So it is 2 times lambda 1 of rho G of gamma C, where lambda 1 is the top eigenvalue of this matrix.
Leo, I think it's previous L2R.
Yeah, sorry.
Thank you, T. So it should be log of the unit.
Lambda 1 is the log. Lambda 1 is the log of the eigenvalue. Yeah, sorry, thanks. So this is the point of view that one may take to generalize, right? So if now let gamma, you find a generated one hyperbolic. And I take G to be a semi-simple group, and so I have a Cartan projection, a Jordan projection, sorry, that we already saw appearing many times. And the point is that for an Anosov representation, I can just pick a function and compute some length in the same way. Okay, so let me see if this.
I have a question. So about the path metric.
Yes.
So the Thurston distance is not symmetric.
Yes.
But then you're saying it's a path metric of
The norm is not symmetric as well. The norm of B is not the norm of minus B.
But is it linear otherwise, or it's not linear?
What do you mean?
Like lambda, if you take a vector, that's
If lambda is positive, yes. Yeah. So now what I will do is I will consider a space of representations, and I will fix a function, and this we already seen appear many times in this conference, and compute the length with respect to this function. Right, so I will let just, I don't know if we already have a notation for this, but I will denote this will be the so conjugacy classes of theta Anosov reps. Right, so I will pick a functional in A star, and for a given representation I can compute this number, which takes some conjugacy class or some element into the group, and I just take the Jordan projection of this and evaluate on my function. And of course, if I want this number to generalize some sort of length, I need to assume that this is a strictly positive number. So what we saw in Andreas' course is that in the setting of theta Anosov representations, is you pick your functional very carefully, then you have a lot of information about these numbers. So, but before going to that, let me just mention that I could just, given this, I could just say, okay, why don't I just define the metric to be the sup of these numbers for two given representations? So naively, we could define dth phi, rho 1, rho 2, to be the log of the sup, where gamma of L rho 2 phi of gamma over L rho 1 phi of gamma. But the problem is that this number can be negative, okay? Because there exist concrete examples of representations rho 1 and rho 2 for which you have strict domination, okay? So this is due to Tolosam, at least. let me just mention this name. So we saw that this cannot happen on Teichmüller space because you have a constant entropy feature, right? So what we do is we normalize by the entropy, okay? So we define this number, which we have seen appear yesterday. Maybe. Yeah, sorry, I didn't. Yeah, I'm sorry.
No, don't be sorry.
The lim. Sorry, this is in Spanish. Lim t. So you take the number of conjugacy classes. So the same definition, right? It's so one thing that Andres proved is that if you pick your functional correctly, right? So this there is this whole construction about you. So you consider the center of the parallel set associated to theta. You consider a functional. You consider the projection of the limit cone there, and you ask this functional to be strictly positive in there. But so this is strictly positive and finite. So given all these conditions, this is strictly positive and finite. All right. So this is Sambarino. So now I can renormalize by entropy. Okay, so I can put these factors here. And this will be my definition of the Thurston metric. And by the same argument I sort of outlined for the Teichmüller space gives you that this number cannot be negative. Okay. So where am I? Yeah, I think this one. So this cannot be negative. And of course, satisfy the triangle inequality.
What is the assumption on phi?
Right. So I have to, yeah. So I have to consider this space A theta star, which is the dual of the center of the stabilizer of the parallel set associated to theta. Project the limit cone there, and I take a function which is strictly positive on there. Okay. We will see concrete examples in a minute. Okay. So this is maybe just want to take that theorem and then right. So the theorem. So as I said, there is. I mean, it's not by running the same argument I gave in Teichmüller space. This number is greater or equal than 0, and it satisfies the triangular inequality. Okay, and so the theorem is that if two reps have distance 0, then I cannot conclude that the representations are conjugate. So I can give a weaker conclusion, which is that the renormalized spectra coincide. Okay, and this is right.
You mean coincide for all gamma?
Yes, always. Yes. Okay, but the thing is that. So is there a question about the statement or?
Can that happen? That seems unlikely to happen a lot.
Yeah. Okay. So I think that we have a good understanding of when this can happen. So, I mean, I think that this has maybe long history, right? But so I will throw out some names, and probably I will forget others. I'm sorry. So maybe I will mention Burger, Dalbo, Kim. So maybe Kant. Maybe BCLS as well. So they say to you, if you have some good control on the Zariski closure of your given class of representations, then you sort of, so with, let me say with good control, control on Zariski closures. Then you can show that this condition implies, so you apply Benoit's theorem about the non-emptiness of the interior of the limit cone to see that, to show that there exists an automorphism of the Zariski closure. So I will denote the Zariski closure of G1 by this, and the other one by this. That extends the, so that takes one representation to the other. Okay, so it takes row 1 to row 2. So I plan to spend some few minutes explaining how to apply this in a concrete setting to show that in some concrete settings you can sort of say, so for some choices of classes of representations and functionals, you can really conclude that the representations are conjugate. So this automorphism is inner. And in some other contexts where you cannot conclude that, just say how they must differ, right? So let me give these examples.
What is G?
The Zariski closure. So G rho is the Zariski closure. Thank you. Okay, so some examples. I mean, for many of the classes of Anosov representations we already encountered this conference, we have good control on Zariski closures, right? So I didn't say what is this good control. Okay, but let me just explain very concretely how this works in an example. So I will consider hitching tree of S, right? So we already saw that this is a connected component of the, so this is contained in the space of delta Anosov representations, surface group into PSL3R. Okay, and I have to pick a length function. So we'll pick the first length function I will pick is a root. Okay, so just to fix ideas, let me pick the first simple root. So this will be my phi. Okay, so lambda 1, so alpha 1, sorry, is the log of the first eigenvalue minus the log of the second. And so very nice feature about this is a theorem by Rafael Potri and Andrés Sambarino, is that entropy is constant here. Okay, and another thing is that we have a good understanding of what are the possible Zariski closures. So G rho in this case is either ESO to 1, so it factors through a Fuchsian representation, or it's PSL3. So let's say I take two representations for which this number computed with respect to the first root is 0. So I have this general statement which tells me this. So you see, in this concrete case, I don't have entropy factor. And if it happens that the Zariski closures are SO to 1, this is just marked length spectrum of hyperbolic surfaces. Okay, so let's assume it's PSL3R. So assume PSL3. So we have this general result by these people that says the two representations are Zariski dense, and there is an automorphism between them, and there is a list of possible automorphism, right? So I want to conclude that this automorphism is inner. The representations are conjugate, but there is an exception. So it could be this. It could happen this. So the automorphism group PSL3R is generated by. So is this guy, the identity, and then inner things. But so you see that if it was the case that this would happen, if you plug the fact that you are assuming that the lengths are the same, you would obtain, so this is a small computation, you would obtain that lambda 2 of say rho 1 gamma has to be 0 for a gamma. And this is not possible because this would mean that the limit cone has empty interior, and I'm assuming that the representation has Zariski dense. So this is very nice. For the first root in heating component, I have a true metric. I have no entropy factor. Right. So the problem is that, yeah, I mean, I want to do some geometry with this, and I don't know how to read the root in some sense. Right? It's not clear what would be some sort of analog of Lipschitz thing if I use this length. Okay. So let me pick another length function.
You say that the distance between the representation and the convection line is 0?
In this case, no. But in what I will say, yes. So if I pick the root length, if I have distance 0, then they are two different. They are distance positive. But now I will pick another length which has this property. It's more geometric, but has this problem. Okay. So another possibility, instead of picking the root, so right, so I put an A for the case of the root, and I will put a B for the case of the Hilbert length, which is lambda 1 minus lambda 3. And this is very geometric in the sense that really generalizes the picture that we see in Teichmüller space, right? So if I have a homotopy class of curves, there is a unique Hilbert geodesic of the underlying projective structure, and this number gives me the length of the geodesic. So there are two issues that appear here. So issues. So one is that you need to gain control on the entropy. Okay, so entropy is non-constant. So this is due to the sum, I guess. Then improve this, and then, okay, so you renormalize by entropy. I mean, this made things trickier, but okay. But the other problem is exactly what you said. So if I compute the length of rho, the Hilbert length of rho, it is precisely the same as the Hilbert length of rho star, where rho star is given by this thing. So rho star of gamma is defined to be gamma inverse transpose. And these two representations can be different. I mean, in general, they are, unless you are in the function locus. But this is the only thing that it can happen. Okay, so this, up to an order 2 automorphism, this really defines a metric. Okay. And so we have many examples of Anosov representations in which we have this control on Zariski closure, so we can run this argument. Okay. I mean, I just gave a highlight. Mm-hmm.
Is there a infinitesimal form of this?
Let me look it up. Yeah, I think this one. Okay. Exactly, yes. This is maybe theorem 2. All right. The second theorem. The point is that we have a very ugly formula because of the fact that entropy is non-constant. But we will see that this formula, when the entropy is constant, it's really the same formula that we already encountered. Okay. So if I have a tangent vector, let's say I am in a smooth point of the space. So define this. So this will be the log of the sup over gamma, and then the formula is horrible. But I want you to keep in mind that if entropy is constant, then it will be the same formula. So this will be the derivative at rho of the entropy evaluated at the vector times the length. So yes, gamma plus entropy times the derivative. I mean, it's really the rule of like the derivative of the product, right? So I think this is this at B, and then H rho phi. so define this number, and we can prove that this number is non-negative.
This is a beautiful formula. It's a bad formula.
So well, it's better if entropy is constant, for sure. So let me just mention that this function is really it is differential. So I have the right to take that derivative. So it's analytic actually. So I am applying BCLS here. So it's a Finsler norm, almost a Finsler norm. So in this very general setting, I cannot ensure that if I have a vector a priori, I cannot ensure in general that if I have a vector whose norm is 0, then this vector is 0. Okay, but so it's okay. So it's then. So this is finite and positive. I mean non-negative. So triangle inequality. So I will write it like this. Meaning that it is homogeneous if I restrict myself to positive scalars. And a condition, if this is 0, then what? So these conditions, which, I mean, so then this derivative at B is equal to minus okay, and these kind of conditions already appear in BCLS paper, right? So they construct a different metric, which is the pressure metric, and so you have some sort of I mean, it's defined at the tension level, and you have some sort of equality like this. I mean, some sort of property like this, right? And in some specific context, they can show that a condition like this implies actually that the vector you are picking is 0. Okay, so let's say for instance, correct me, Hitchin and first root, maybe this is fine, right? Yeah, so it's really the same condition. So you see, if entropy is constant, this is saying this is 0, and you need to ensure that B is 0, right? To have a true norm. But maybe more importantly, like this, then I want to emphasize this. So we don't know how to prove in general that the path metric induced by this. Let's say I restrict myself to a context in which this really is a norm. So I have a path metric, and we don't know how to prove that this coincides with the Thurston distance. Okay, but so we can show a very, very weak argument, very weak property, which is that yes. So how do I write this? So that means if I have a path, a smooth path, representations, then I want to compute this Thurston norm at the initial point. This really coincides with the derivative of the Thurston distance.
Do you have any description of like the unit ball, anything like that, or like with like Thurston sort of like non-unit measure laminations or non-unit?
I mean, I think that this opens up many questions. Yes, I mean, for the moment we have the construction and we are thinking about related things, but I cannot say anything very concrete about it.
This is a similar question, but a little more disorganized. I mean, do you expect it to be polyhedral or really Finsler?
So what is the statement in Teichmüller phase?
So
I'm sorry.
So it's not a polyhedral. It's it has some of these, it has some facets corresponding to like measure laminations that are non-uniquely ergodic,
Right.
but it has some smooth points as well.
Yeah.
So,
Yeah. No.
But do you have example where V is non-zero and the norm is zero?
Yes. Maybe that already. I'm not sure.
It must
It
happen.
already appears for the Hilbert length, or what?
It must happen at the Fuchsian locus
Yes,
in
right.
Hitchin 3, right?
Right. The same. Maybe it's related to this the generality that we saw when you take the Hilbert length, right? And you see there is a fixed point set of this involution.
That's why I have the question.
So I think there is another example for Barbour component. If you take something in the reducible SL2, when you deform in the center, you're not going to change the length.
Yeah.
Right.
Yeah.
Something I learned from you.
I think you might be able to resolve this issue by taking a blow up along, in the sense of algebraic geometry, along the sub thing where normal directions have length 0.
Right. So, proof of the theorem. Okay, so let me call this theorem 1. So I want to point out that this theorem is really a purely dynamical theorem. Okay. So there is this whole machinery developed by BCLS, which they use to construct a pressure metric, and you can sort of change the viewpoint to show that this theorem holds with the same machinery. Okay. So I'll try to explain that. Maybe I should mention here also a work of Guillermo. Nipper and Lefebvre. So they prove a similar thing for a space of negatively curved metrics on a given compact manifold. Okay. And, I wanted to tell you how this statement really fits into the setting or into the formalism developed by BCLS. So what do? You consider a flow. So we consider this flow space, which we already saw many times, seen appearing here. So it's the geodesic flow of gamma. And so BCLS proved that a very important property, which is this is metric Anosov. So you should think about this as a topological version of an Anosov flow, a true Anosov flow. And this implies many things. I mean, we know many things about the dynamics of the flow because of this fact, applying results by
Depends on what you want to prove.
the coding. Bowen. Yeah. Sorry. It tells you many things about the dynamics of this flow. Okay, and so what do you do? So given if you pick a representation and or functional on your given n conditions, so I think this is Sambarino. You get a function, which I will denote f rho phi, which goes from this weird space to a strictly positive function. So that so these flows, the periodic orbits of this flow are parameterized by conjugacy classes of the elements in the group. So when I integrate this function along a periodic orbit, I recover the length. Okay. So this gives me a reparametrization, which I will denote phi rho phi. So it is a flow in the same space, but the orbits I mean, with the same orbits, but they are traveled at a different speed dictated by this function. Okay. So the period for the periodic orbit associated to gamma is this number. Okay. Okay, so maybe the name that I was missing here is the guy who proved that metric Anosov implies that you have the coding. Polycot. Yeah, thank you. So what do now? You pick two representations. Okay, you pick row 1 and row 2. And this gives you two functions, which is the reparametrizing function for 1 and the reparametrizing function for 2. So what I will do is I will take the quotient and this function to be f. So I can think this function f to be in the reparametrizing function for the reparametrization associated to row 1 to the one associated to row 2. Right? So I said that there is one flow coming with each representation, and this one reparametrizes from row 1 to row 2. And so I want to assume that the distance is 0. I want to conclude that. So how do I conclude that out of this formalism? So if one could prove that f is a constant, then because of this, so here let me write this down again. So if I flow with this guy instead, right? So if I do this, what do I want to say? Yeah, it's already written, right? Okay. So if we could prove that f is a constant, then you see that we would get, by integrating along periodic orbits, we would get that this constant times of any periodic orbit should be the length of the second one. And this actually forces C to be the ratio of the entropies. The problem is that you cannot prove that f is a constant, but so to conclude this, you just have to integrate. And if it happens that your function is not a constant, but it differs from a constant by a function which is a derivative along the flow, you get the same conclusion. And this is what you can conclude, right? So what we will prove is that we prove there exists C and there exists a function which is differentiable along the flow, so that the derivative, so I have a flow associated to the first representation. Yes, this. And if you integrate along periodic orbits, you really get that if you show this. So this is the right. Ah. Five minutes? 6 minutes? What? How much? Yeah? Okay. 10 minutes, okay. So I will reinterpret the fact. Right, so, okay. So now I am taking as my base flow, so here the base flow was the Gromov-Geodesic flow. Now I am taking as a base flow the flow of rho 1. And that equation is precisely me saying that if I integrate the function that is going from rho 1 to rho 2, this is giving me the second length. Okay, so actually I can write this down differently. So this integral, I will write it like this. So let me say it. So let delta, so I have to put some things here. So it's ρ1 phi. So this will be the Dirac probability mass at the periodic orbit, this periodic orbit. So if I denote this like this, this equation actually becomes this. So if I integrate with respect to this mass, let me just omit this guy, okay, this notation. This is just L rho 2 over L rho 1. So may wonder so how this disappear. I am taking this to be a proba. Okay, so this is, it takes me L rho 1 amount of time to go through this orbit, but I'm normalizing this to be a probability, so I have to put this factor here. So now my Thurston distance between rho 1 and rho 2, phi here, is the log of the sup over gamma of these integrals. Sorry, the entropy. And this is something which is purely dynamical. Okay, so Sambarino shows that these guys are actually the topological entropies of the flows. This is a consequence of the coding, and yeah, so I'm integrating over invariant measures supporting on periodic orbits, and this is dense over the set of periodic orbits, right? So I can write this down as the log of the sup over invariant probability measures for the flow of this number. So let me just write H2 and H1 for these guys, okay? So I have this expression. This is a topological entropies. This is a potential over a flow, and this is invariant measures. So this is really purely dynamical. Okay. And yeah, so maybe finish here. So what do? We apply this proposition, which is key in the construction of the pressure metric as well, which is there is a specific measure for which you can, this number here satisfies a rigid inequality, okay? So let me denote this number here by J M of F. So basically let's prove that if I compute this number with respect to the Bowen-Margulis measure of the flow, so this is greater or equal to 1 with equality if and only if F minus C is a derivative along the flow. So when you're taking this sup, this is for sure bigger than this, right? The log of this. So if you assume that the distance is 0, then it actually forces this guy to be 1, and you have this conclusion. So to finish, I will just say a few words, just say it out loud, so because I want to emphasize a bit the difference with the pressure metric, right? So because of this argument, you can take you can say, okay, so I have this function that takes a minimum precisely when I am in my representation rho 1, right? So you take the Hessian of this, and this BC. Let's prove that this gives you a Euclidean norm, which is positive semi-definite, and in some situations they show it is definite. Okay. So they do this. Let me repeat by taking the second derivative of this number. So integrate with respect to a specific measure and take a second derivative. While what we do here is we integrate with respect to all measures. And the infinitesimal statement I gave is saying that we are taking the first derivative instead. Okay, so this is the difference between the two things. Thank you.
Question? Go ahead.
Do you have any idea what the Bohr function boundaries for these things look like? I asked because Walsh has Bohr function boundary of asymmetric matrices on the Thurston.
So I think we gave it a thought about this at some point, but I don't remember what. I mean, I don't think we have nothing very conclusive. I don't know if Leah is here. Yeah, I cannot say. I mean, we certainly posed that question to ourselves, but didn't manage to say something.
Question.
In the Thurston story, the soot is realized by lamination, right? Mm-hmm. So what happens here? So maybe let me just say this: we know nothing about the construction. Okay, we're working on trying to prove similar stuff as Thurston did. Situation where you can say what realizes the
maybe. I mean, we have been focusing mainly in the question of trying to build these geodesics, which is a key ingredient to show many of the properties. So in particular, I think, maybe I'm saying nonsense, but to show that the path metric is the metric, I think that if you find geodesics, you're fine. So we're focusing more in that part, but it's for sure. I mean, it's a very natural question. I mean, yeah, there are many questions. Yeah.
So is there some similar property like taking the supremum only over the simple?
Yeah, that's the question that he asked. We don't know.
Okay. And also, is there some similar notion of Lipschitz method on this?
We are working on that, but I don't have nothing very conclusive to say. Yeah. Yeah.
For each phi in A plus delta star, you have such a metric.
Yes.
Can you compare them? Is there a better one? Or?
So yeah, I never thought about that. I mean, there should be some sort of be something thing between the two, maybe, or maybe not, because the length is sort of comparable to the translation length in the translation length in the group, I think. So maybe you can produce some very coarse estimates, but so your question was.
Is there a better one? For instance, take all the Finster norms associated. You take a vector V, take the supremum of the Finster norm among all the phi you may consider. Are you sure it's positive, for instance, if the vector is not zero? Okay.
But okay, I have to think about it. Maybe it's not impossible, but to show it's positive, yeah.
If it's not zero.
Yeah. Let me think about it. I don't know. I never thought about it. Yeah.
Question? Thank you again.